Eric Boles, Center for Ag and Rural Sustainability. Filling in for Dr. Matlock. He couldn't be here today. He sends his apologies. On this presentation, I have to give credit to Dr. Matlock and Dr. Greg Thoma. Dr. Matlock is the director for the Center for Ag and Rural Sustainability. We like to call ourselves CARS, Center for Ag and Rural Sustainability, and that is his mission. And Dr. Greg Thoma is in the Chemical Engineering Department at the University of Arkansas. And both of them have had a hand in all the work that I will be showing today. It should be a pretty light presentation. Hopefully it won't be too scientific. Won't get into too much of the nitty-gritty, so you can digest your breakfast and wait for the coffee to kick in. All right. Everything is connected. Everything is connected. And I'm sure all of you already realize this, but you have ecosystem services here on the left. Ecosystem services include everything from nutrient cycling to air quality, water quality, climate mitigation, and then these ecosystem services that we take for granted. Any plot of land, any untouched plot of land is producing ecosystem services as we speak, and we take them for granted, and we don't have to pay for them. But these ecosystem services are what allow us to live the healthy, wonderful life we live. And these ecosystem services are essential to, the life we live and good health on this earth. Everything is changing. I love this one. So everything is changing, and it's always been changing, but it's been changing at a slower rate. Now, the rate of change is increasing exponentially fast. And I borrowed these slides from PBS's website, NOVA. I'm sure you all heard of NOVA, but it just paints the quick picture of how quickly change is occurring, especially population change. And so 2,000 years ago, at year zero, we had 3 million people on this earth. All these little dots represent approximately 1 million people. 1,000 years later, the population increased as much as 10 million. Went from 300 million to 10 million, or to 310 million in 1,000 years. 800 years later, we had our first 1 billion people. And then 127 years later, we had 2 billion people. 33 years later, we had 3 billion people. 14 years later, 4 billion. 13 years later, 5 billion. 12 years later, 6 billion. And so that rate of change, it's just exponential. In the first it took us 1,800 years to reach 1 billion people. And now in the course of 12 years, we gain it by 1 billion. The total world population. And so 50 years from now, roughly 50 years from now, we're talking about 2050. This is a little bit old. That's more like 38 years from now. But in 2050, we think there will be 9.25 billion people. Here's a graph of that. So this little dip right here, the Black Plague, that's the only, other than that little divot called the Black Plague, we pretty much have exponential population growth. And this is predicting if fertility rates, if we continue at the growth that we're at, and fertility rates stay the same, we will reach 11 billion people by the year 2100. But we don't think that's really the case, because, think back to your basic microbiology course that you may have taken at one point in time. So when you have, when you have bacteria growing in a petri dish, or when you have or whatever it may be, when you're growing bacteria, the rate of growth will look just like this. Except what happens? It can't continue on this exponential growth. At some point, there reaches a boundary, a limit, a limit, and that limit, we're limited by resources, by food, and by space and resources. We think resources, food, will be our population limiter, and we will max out at 9.25 billion right here. 9.25 billion. So, and this is just laying out the initial problem. And I think it's a great, I'm glad I got to speak first today, because I think this is a good intro into everything else you hear today, because knowing where our population will reach in 2050 is essential to us designing our food systems and the food supply chain in a way that we can meet the demand at that mark. You know, assume that we might reach that we will reach 9.25 billion, and then plan accordingly. So here's the United Nations. I think this is actually a study they did in 2005. It's a little old, but the United Nations predicted that population. So this is the curve. If fertility rates continue as is, this is a median estimate, probably the most accurate estimate, which puts us at about 9.25 billion. All right, and so what we do in the next 10 years will shape the world of our future, and that 10 years is so much more important than that next 10 years is equivalent to the last 100 years. Because like I said, the rate of change is increasing so quickly that our problems are occurring faster, and our solutions to those problems need to occur faster. We need to come up with solutions at a faster rate than ever, and we don't have as much time to piddle around and maybe make the wrong choices as we once did, because this rate of change is exponentially occurring. And then this last line, I like this. When technology and culture collide, technology prevails and culture changes. You can think about that for a moment. And it's so true. All right, we're all in this together, and that is the truth, and it's an important concept to embrace, because so the more developed regions, including the United States, our population level will stay pretty much constant. Our fertility rates have decreased. All this growth, I haven't mentioned this yet, I should, but we are about 7 billion right now. Everybody knows that. We're at about 7 billion right now. So we got 2.25 billion to go, we estimate. And so all this growth from here to here is going to come from less developed regions. You know, countries with higher fertility rates, and that's going to be 2.25 billion more people coming to the dinner plate every night. You know, we got to find a way to feed those people, because we are all in this together. So this is a map of the world that shows the pastures and croplands of the world, and so you can see, you know, where have we not filled in with pasture and cropland. And this is the largest biome in the world, represents over 40% of the world's space, of our land, not of the world's space, of our land surface area. Over 40%. And the areas that aren't covered are because we cannot. I mean, we've exploited all the arable land, all the land that you can grow something on or raise animals on. We pretty much maxed it out. So the only gaps in here are areas without water and without resources. And then a few of the other gaps, we got some down here. This is very arable land, but it is actually rainforest, and so that's why we are digging into that rainforest more and more each year. And so we've kind of, at last slide, I painted the picture of, we've pretty much reached, you know, the largest biome in the world is crops and pastures. And so we really don't have much more room to expand. The only place we have to expand is rainforests. And then you're losing biodiversity, and you're reducing those ecosystem services that I started out talking about. And those ecosystem services are so essential to our way of life, and it is not a good idea to dig deeper into those rainforests. And so we have to do more with the land that we already have. We cannot increase the farm footprint any larger. So this is Jason Clay from the World Wildlife Fund. He devised this, I think this is also a study from 2005. He came up with this, Freezing the Footprint of Food. I love that title. And this concept is, so with the same amount of land, to feed all these people, we need to produce 3 times as much food. We need to reach 300% we need to get 300% more efficient. We need to produce that much more food on that same amount of land. And this is how we're going to do it, says Jason Clay. We can do it with improved genetics, decreasing poor management practices, so through better management practices, increasing technology, removing underperforming lands or improving the productivity of those underperforming lands. Property rights, that's a huge one. People are growing food on land they don't even own, so why would they be motivated to really make that land more productive? Waste, we're wasting so much waste. Overconsumption, that'll also help us to reach this goal of 3 times improvement. And so the role of research is all of these. And so that's why the land-grant universities need to be continuing research and improve upon those categories so that we can feed the people of the future. All right, so to reach these goals, the first step is measuring, getting a benchmark. Where are we at right now? So these are a few just basic definitions. We got metrics, quantifiable phenomena to measure an endpoint. Indexes are made up of metrics. So a metric is measuring CO2 gas. Well, an index is measuring the global warming potential of those gases. So more an end result. So metrics are used to make up indexes, and indexes are what we're really worried about. Baseline, like I mentioned, measuring sustainability is essential because we have to benchmark, we have to figure out where we're at right now so that we can make improvements. And a tool that we use to do this is life cycle assessment, LCA. You'll hear me say LCA more and more. And that is what my research is about. Who here has heard of life cycle analysis? Half the people, maybe more. Maybe some people the coffee hasn't kicked in yet. Well, I do a lot of work with life cycle assessment, and I always wonder how many people know about LCA work because I hear about it, 30 times a day, and it's funny when you're living that life, you get in your head that everybody knows everything about this, but it's not always the case, and so try to always ask that question. And then we have standards for life cycle analysis work, and if you still don't know what LCA is, I'm about to go into that. All right, sustainability is a multi-metric, and here this was done by Rockstrom in an article in 2009 in the Nature Journal, and what we got here, so this is a radar diagram we call it, and this green circle in the middle represents, so the world, those ecosystem services have the ability to restore and to reach an equilibrium within the world that we live in, and the world the Earth, those ecosystem services are able to accept a certain amount of pollution, right? There's a certain amount of pollution we can put into the world, or there's a certain amount of impact we can have without dire consequences. The world's good at taking care of itself, really, as long as we don't have a huge impact. But here you can see, so these are some of the metrics that we are measuring, and like I mentioned, a metric would be climate change caused by CO2 or methane or whatever it may be. And so we got climate change, ocean acidification, stratospheric ozone depletion, nitrogen, phosphorus, global freshwater use, changed land use, biodiversity loss. You get it, these aren't quantifiable yet. But the ones that we're really hearing in right now, says Rockstrom et al., are biodiversity loss, those losses of rainforest that I was mentioning. That is a huge loss of biodiversity. We're losing cures to diseases that we don't even know exist. But loss of biodiversity makes us just less able to deal with the problems of the future because we're losing resources, and resources are obviously very, very valuable. Climate change, we're heard in there, and nitrogen cycle, very bad. Nitrogen is a non-renewable resource. So the tool that we can use is life cycle analysis. And I love this slide as well. So the stages of a life cycle analysis are we set the goal and we define the boundaries. So we decide, assess the problem, figure out what you're trying to accomplish, what you're trying to measure, and define the boundaries. And then the next step, so this life cycle analysis will be done of a particular product, say, your coffee cup. And so the next thing you got to do is figure out what all has gone into and out of the production of that coffee cup. So that is the inventory analysis. You're tallying up all the inputs and outputs of that coffee cup, of the production of that coffee cup, and for the whole life cycle, hence life cycle analysis. And then impact assessment. Impact assessment, we are measuring, for all these chemicals and greenhouse gases we use to produce that coffee cup, what are the impacts? And then we interpret all this with any scientific work, what's all the data without interpretation and drawing conclusions, because that's the real goal of this, is to interpret and come up with conclusions that can improve product development, allow for a better planning of the future, better public policy, marketing, other catch-all. All right, why life cycle analysis? Well, our economy isn't doing very well right now, and life cycle analysis is looking at the whole life cycle of a product. And by looking at the whole life cycle of a product, we are able to determine inefficiencies in the production and disposal of that product. And by finding inefficiencies, inefficiencies are money lost, money wasted. So by finding inefficiencies, we can make our economy better and stronger. Resource conservation, once again, efficiency. The same resources that hurt, or the same resource losses that hurt the environment can also, or do also, cost money. So by saving money, we can also save the environment. They go hand in hand. And consumer care. The other reason why we do consumers care. The other reason why we do life cycle analysis work is because consumers want that. There's a big push for green products right now. And so to make your brand name or your company more sellable, you have to, meet those desires of the consumer for your product to be more sustainable. And by doing a life cycle analysis, determining the inventory of greenhouse gases or determining the water footprint of your product, you're able to establish a proactive position towards sustainability. You can make that statement that we tallied up our greenhouse gases, and over the course of the next 5 years, we are going to reduce those by 20%. And customers like that, and so that sells and that improves the economy. All right, life cycle analysis to understand and manage the supply chain process. This is I've already mentioned this, but so we break the life cycle of a product down into all these unit processes. Each unit process. Let's use the example of this unit process. Imagine this is your sink in your kitchen. And I had breakfast this morning. I made some dirty dishes. So you had got those dirty dishes, and those are your input into that sink. Well, to clean those dishes, you need inputs from nature, namely water. And your input from another process would be dish soap. That dish soap has had all kinds of different things, has already been through lots of processes. But we got dish soap and dishes coming in, and we have water coming in. Well, going out to nature, we have water, but also we'll have some dish soap at this point, and everything that is encompassed within that dish soap. And then our outputs to other processes, to the next meal, is your dishes, right? So these unit processes make up life cycle analysis. Life cycle analysis is made up of many unit processes. And it seems, sometimes you think about the life cycle analysis of a product and it seems like take two materials, combine them together, or 3 or 4 materials, combine them together, and you get a product. But actually it's much, much more complicated than that. Once you get into it, you realize that there's all these unit processes, step by step by step, that go into this. And not only that, you can have an infinite number of unit processes if you do not draw a boundary. Think about the production of that soap. That soap was created in a processing plant, and so you can have the impacts of that processing plant, but also you can have the person say, I work at that processing plant. So are you going to consider the impact of me driving to work as part of that greenhouse gas impact? And if I'm driving to work, I drove in a car, so are we going to include some of those car resources, the creation of that car, into that life cycle analysis impact? Well, that's why it's so important to draw boundaries. You got to draw a boundary early on and say that, you have to draw a boundary early on for obvious reasons to make the life cycle analysis process work. Boundaries matter. All right. Another big issue with life cycle assessment or analysis is allocation. All right, so you got a chicken. This chicken, you process it. You process a chicken, and you get the legs, the breasts, the giblets, and you can set, if you're trying to do a life cycle analysis and determine the impact of breasts, you could say that that the other parts of the chicken should not be accounted for. So if you just want, if I'm just trying to get breasts to a dinner plate, then that should only be a certain portion of the total impact of the chicken. All the greenhouse gases that went into producing that chicken should not be included in just the production of the breast. So you can allocate by mass, or you can also allocate by weight. And so you got this chicken coming in, but you also have all the feathers and the feet and all the skin. I forget the technical term for this. I'm sure it's not many of you know, but this can be used for pet food, right? Can be used for many things, but pet food is one. Well, somebody who wants pet food, should they, and they're doing a life cycle analysis of their pet food, should they be held accountable for all the greenhouse gases produced by the production of the entire chicken? We say not. They should only be responsible for the greenhouse gases produced by this portion of the chicken, not this meat. This meat is worth much more. This is pretty much the byproduct, the waste product. And if you count by mass, this can be a sizable amount. But if you account by value, by the monetary, the economic value, then this becomes very small. So a very small percentage of the total greenhouse gas production of the chicken. So allocation is very, very important in life cycle analysis work. I hope I explained that well enough. That's a little bit trickier concept to wrap your mind around. All right, and when dealing with greenhouse gases, so CO2 is not your only greenhouse gas. Actually, CO2 is not one of the more potent greenhouse gases. Methane, 21 times more potent of a greenhouse, more effective of a greenhouse gas than CO2. N2O is 310 times more potent of a greenhouse gas than CO2. Well, so this is why it's important for us to not measure the amount of CO2 used in a product, but to use a metric, not use these indexes, but use a metric called the global warming potential, or the equivalent CO2. So then if you have 1 gram of CH4, we'll actually call that 21 grams of equivalent CO2, so that we can have 1 unit, because you need this 1 unit to measure the impact of products. Emerging consensus on LCA, need for comparable. This is some of the standards we're coming up in life cycle analysis work. It's relatively young, and I'm just going to skip through that. That's tedious. We got major challenges in the food system. I love this part. So consumers are far removed from producers. And that is so true. You know, people don't even know where their food's coming from. Yeah, they have no idea. And I'm sure I don't know as much about as many of you. But consumers are far detached. Complexity of the supply chain results in ineffective feedback systems and irrational decision making. You know, the supply chains are very complex, and they can lead, if we don't understand them, it can lead to poor decision making. And volatility of food prices, and the future of prosperity depends on the stability of our food system. This is a basic layout of our food system. We've got production to processing, distribution, direct marketing, wholesale or retail, and consumption. This is you or I at the bottom. Actually, I'm sure many of you are more involved in the production and processing. And we need safety, security, and stability for this food chain. All right, this will be an example of some of the work we're doing at the U of A involving the carbon footprint of fluid milk. And that this research is funded by the Dairy Association. So calculating the carbon footprint requires you got to account for all levels of greenhouse gases emitted within the different processes of the supply chain. We got energy consumption, manure and nutrient management, huge, got to account for that. The system begins with extraction from nature and includes package disposal, cradle to grave life cycle analysis. Life cycle analysis is a tool that is commonly used as framework for these calculations. All right, so in life cycle analysis, we have standards, and these are set by the International Organization for Standardization, the 1444. You all don't care too much about that, but the goal of this study was to determine the greenhouse gas emissions associated with the consumption of 1 gallon of milk. And our scope was cradle to grave. Cradle to grave is, you know, the very beginning of the life cycle to the very end, the grave, the landfill, whatever it may be. All right, and here's a basic layout of this supply chain. So you got production of the feed and the cattle, to processing of the milk, to distribution of the milk, to consumption of the milk. And we're trying to determine the greenhouse gas for all that. And this elaborates on that system one step further. Then you get into crop production, milk production, transporting. We also include the transportation of these products to the different steps. And that lays out the supply chain. The life cycle inventory, as I mentioned earlier, the first step to completing a life cycle analysis is you have to inventory all of the inputs and outputs. We did that with surveys and literature. Major assumptions. It's so important to keep this work transparent and to list all the major assumptions. So infrastructure was excluded. So you got a processing facility. We don't include the impact of the the building of the process facility. We would not include that in the greenhouse gas production of creating a product. Biogenic carbon, this is a really interesting one, I think. So sequestration is not included. We don't account for that, and I'm sure all of you have heard of carbon sequestration. Well, all these animals are being fed crops, right? And these crops, when the crops grow, they grow with CO2, right? So they are sequestering carbon from the atmosphere, and so you could say that that's a positive carbon impact of feed production and cattle production, cattle production in this case. But so biogenics. And you also don't include the respiration, so I'm working at a processing facility and I'm breathing, so you don't include that CO2, that's negligible. But that's kind of interesting stuff, and we might see changes in that in the future. Economic allocation, I spoke of allocation earlier. Product loss, that's kind of an interesting one. So we assume that we lost 12% at retail and 20% at the consumer's plate. These are some of our results. What you should see here is milk production, really high. So these are the total greenhouse gas emissions. Total greenhouse gas emissions for 1 gallon of milk. So what you see here, milk production, really high, really high. The milk production includes the feed production and the cattle production. So mostly the feed and the cattle. And the cattle, we got the purple enteric, so the gases going on in that cow's stomach, and the production of CO2 from that. And then we also have manure management. Manure and enteric gases are really the leading producers of CO2 equivalents of greenhouse gases in milk production. And then this breaks it down a little bit more. It shows that methane, the red is methane. Methane is a huge contributor in enteric and manure management. And then this pretty much shows the same thing, and it represents that, pretty much 50% of the greenhouse gases are coming from manure management and methane from within the cow. This shows the big picture, and it represents our allocations, and it also shows all the inputs. One thing interesting about this is like transport. Transport's really not a big greenhouse gas producer, which is contrary to popular belief, I'd say. Yeah, we keep finding again and again in these studies that transport really isn't playing that large of a role, which goes against the buying local, or shows that it's not as large of an impact as we once had thought. So overall takeaways: do more with less. This is obvious. Improving efficiency, innovation, technology transfer. Innovations can be made in manure management and nutrient management. Operations with a smaller footprint generally have adopted better management practices. So we got I'll put in a quick plug here for the University of Arkansas and Dr. Marty Matlock's work, who I work for. He has a bunch of sustainability initiatives going on. The Sustainability Consortium, Field to Market, and the Sustainability Consortium are the big ones. What's so interesting here is we think that the metrics should be based on outcomes, so reducing global warming, but the technology should be neutral. We all agree on that. Technology should be neutral, so we should not define the kind of technology you reduce your greenhouse gas emissions by. The goal is just to reduce global warming, and we believe that's best for the producers to make those decisions. We kind of set the standards, and then producers, the ones on the ground floor, are the ones who really know what's going on and how to reduce that. And then, so the field of market's made up of many not just huge corporations, but a collaboration between many different partners. And then we'll just have to skip through this stuff. I hate to do it. Alright, we shall never achieve harmony with land any more than we shall achieve absolute justice or liberty for people. In these higher aspirations, the important thing is not to achieve but to strive, by Aldo Leopold. I think that's a very true statement, very valid.